Good afternoon to one and all. Respected HOD, Triple E Department, Faculty Coordinator, Guest Speaker, my dear friends. A warm welcome to you all. We are happy to introduce Student Seminar Series to inculcate the multidisciplinary knowledge in science, engineering, and technology. The series shall invite the talks by the students of BTech, MTech, and PhD from any premier institutions worldwide. The intent of the triplets is to provide a platform for the students to develop their research skills. Now, I hand over my mic to Seminar Chair.
Good afternoon to the dignitaries presented here and one and all. Myself, I'm Chandrika from PUC 1. Now I'm here to introduce our guest speaker, Mr. Siddharth Pilli. Siddharth Pilli is a 15-year-old Indian, Asia's youngest data scientist, speaker. He has addressed over many schools, universities, colleges across India. He is also spreading his knowledge by giving online classes based on AI, ML, and Python as well. Siddharth currently works as a data scientist and a brand ambassador at Infinity Learn, an edtech company by Sri Chaitanya, which helps students on achieving their dreams by cracking competitive exams like NEET and JEE. Siddharth is also currently working as a freelancer, where he provides services on boards and AI solutions to a US stocks and finance advisory company called Right Choice USA. Siddharth is a media personality, having been featured in NDTV, BBC, 99 TV, ETV Telangana, ABN, Deccan Chronicles, and featured in front page of Traveler's Time, and was invited for radio talk show on Telugu NRI Radio, just to name a few. He has been honored as Asia's youngest data scientist for working as a data scientist for a company at 12 years old. He has been awarded as Whiz Kid by Sri Chaitanya Institution's founder, Dr. B.S. Rao, Baiju's Young Genius Award by News 18 TV, and he also has been awarded many more prestigious awards. He also previously worked with IIT Hyderabad on a deep learning computer vision internship, developing computer vision projects for the agriculture field. And currently, he is working with IIT Hyderabad as a research engineer. So, our students are eagerly waiting for your seminar, sir. So, without wasting our time, let us start the seminar. I'll hand over my mic to our guest speaker, Mr. Siddharth.
Thank you. I'll just share my screen really quick. Hopefully, my screen is visible. Let me do something. Just give me a second. Sorry. Hello everyone. My name is Siddharth. My name is Siddharth Pili. I'm currently working as a data scientist. Sorry, this is more audio problem. Sorry. So I'm currently working as a data scientist at Infinity Learn. I'm also currently working as a triple ID research engineer at triple ID Hyderabad and currently in Gachibowli. And I also work as a freelancer. So right now, basically, do some automation bots for financial services. Anything ranging from stocks to options trading. And I'm also giving online classes for Python, machine learning, data science, deep learning, computer vision, and all the good stuff. This is our today's agenda. Today's session is a brief introduction to what is actually artificial intelligence, subsets and scope of today's AI, history of AI, machine learning versus deep learning. We'll understand what exactly is machine learning, what is deep learning, and what differences are there between machine learning and deep learning. I'll help you all understand the inner workings of deep learning, how exactly a neural network works, different types of applications and fields of deep learning. I'll give a small introduction into what computer vision is. I'll explain the 2012 computer vision revolution, ImageNet, on why exactly it was created, and what benefited from 2012 for deep learning in computer vision. And then I'll help you guys understand the skills needed to get a career in the field of deep learning and computer vision. So hopefully by end of today's session, you all will be familiar and understand with all these concepts here. So first, introduction to artificial intelligence. So right now, when we talk about a very broad concept like AI or machine learning, there are at least a bazillion number of definitions that people can come up with. But because of how many times the word AI has been used around, the actual definition of it has been lost in the words. So these are a few definitions which I found, but I'll give my official definition later on. But one definition we have is by John McCarthy from a 2004 research paper on AI. It is the science and engineering of making intelligent machines, especially intelligent computer programs. It is related to the similar task of using computers to understand human intelligence, but AI does not have to confine itself to methods that are biologically observable. What John McCurdy is trying to say is the whole concept of AI or machine learning really is it's the science and engineering of trying to make these sort of intelligent machines. But we're not actually trying to program it really. We're not actually giving each and every specific command to make that intelligent machines. But we're sort of using that data to understand those patterns to make that machine intelligent. But AI here doesn't have to confine itself to methods that are not biologically observable. So that's what John McCarthy coined as the term definition of AI in 2004. And we also have another definition by Merriam-Webster. Merriam-Webster suggests that AI is a branch of computer science dealing with the simulation of intelligent behavior in computers. Now, the second definition might be a little more easier, but by far what my favorite definition, or at least a good understanding to what AI can actually relate, is this. AI, or artificial intelligence, is a branch of computer science that focuses on building and managing technology that can learn to autonomously make decisions and carry out actions on behalf of a human being. Is something wrong? All right, now, yeah. So, artificial intelligence is mainly the ability of a computer program to learn and think. John McCarthy coined this whole term. John McCarthy coined a whole term called artificial intelligence in the 1950s. He said that every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that a machine can be made to simulate it. An attempt will be made to find out how to make machines use language, form abstractions, and concepts, solve kinds of problems that are now reserved for humans in improving themselves. Now, in the concept of AI, now AI, as we said, they carry out actions on behalf of a human being. So when we talk about actions, these can be something which we do in a real a daily life, which can be helpful, and these actions are just carried on behalf of human beings. It's just simple things as object detection. Now, we as humans have great object detection because we know how exactly objects look like, and we can make a classification based on what they are. For example, if we see sort of a car in a road, we know it already that hey, this is a car, or this is a car, so I can classify this object as a car. And if we see a bicycle which is riding on the road right now, we can identify what that sort of object is and come to the conclusion that this vehicle or this object is nothing but a bicycle. And we know this because we humans are great with sort of the whole concept of object detection and classification. And AI, because of its whole concept that it focuses on building and managing this technology, the end of the day, try to carry out actions behalf of us as a human being. AI can also predict and classify what different types of objects are as well. So if you were to place sort of some AI machine on the road, this sort of machine can classify and probably do some object detection to identify each and every object and vehicle in the road. And AI does not just stop there. Translation. Now, we as humans know how important translation is, right? AI translation simply applies machine learning to languages. Now, this goes well beyond standard machine translation, which directly translates every word, often leading to serious misunderstandings. Instead, AI tools can understand phrases, tones of voice, complex sentence structures, and even jokes or slangs. That's one of the reasons why you see AI sort of mastering this whole concept of languages right now. Because if you as a person were to travel to any other sort of place, let it be something like some other country or some other town, city, or let's say another state in India, you might actually feel that the local language of that specific locality might be a bit hard to comprehend. But by using something like Google Translate, we can identify what exactly that language is and what exactly they're speaking in that language. So AI is helpful to us in many ways, and this being one of that. Subsets and scopes of AI. Now, AI is, like I said, it's a very broad concept. Now, AI being such a broad concept, it has few subsets to deal with. One being machine learning, and another subset of machine learning is deep learning. Now, hopefully we got a good understanding to what exactly AI is, because from previous things we understood AI is sort of this branch of computer science that focuses on that basically tries to autonomously make decisions and carry out actions behalf of a human being. Basically, it basically mimics our understanding of making decisions and carrying this whole actions by using data and AI statistical learning algorithms to build smart systems. This machine learning system can automatically learn and improve without being explicitly programmed. So basically, what exactly happens is we don't need to do any sort of programming. We don't need to write sort of a script or anything. It automatically tries to use this data to basically sort of solve a problem or to replicate an action as well. And few examples of AI right now can one be a recommendation of systems of music and various video streaming services are few examples of machine learning. And these machine learning algorithms are classified into three categories: supervised learning, unsupervised learning, and reinforcement learning. So right now, if we see, we have some popular streaming platforms like Netflix, Prime Video, and etc. And also we have some we have some sorry we have some famous like music streaming softwares as Spotify, Prime Office. Try to understand what sort of musics and movies we listen to and watch to, and based on and based on this content, it can give us predictions based on what we may actually watch in the future, or what we actually want to watch as well. But that's mostly about what machine learning really is all about. And machine learning sort of works in this process way, where if we want to train a simple machine learning model, first we have to gather some data. To gather this data, there are many sources of data from where we can gain based on the problem case statement. Let's say we want to predict weather, so we want to create a machine learning model that predicts the weather. So we first gather some data, mainly revolving around different types of weather forecasts, maybe from past 5 years of weather forecast. That's sort of some data which we can gather. And then here comes the part of data cleaning. Now, Sorry. So yeah, sorry. Yeah, sorry. Actually, I have some. Yeah. So yeah, collecting data gathering. Now again, we have to basically collect some weather forecast right now. So let's say again, we wanted to train a weather prediction model. So for that, we have to gather data that belongs to different types of weather forecasts. So for that, as you know, machines initially learn from the data that you give them. It is the utmost of importance to collect reliable data so that your machine learning model can find the correct patterns. Now, this quality of data that you feed to the machine will basically determine how much accurate the model is. If you have incorrect or outdated data, you will have wrong outcomes or predictions which are not really relevant. So basically, they're irrelevant. So make sure when you're collecting any sort of data, you use it from a reliable source. That's the first part because when you want to train a machine learning model, you have to collect the data and gather it. And the second part, the second part, preparation of data. So the preparation of data, you can just think of it coming under the data cleaning right now. In the preparation of data, we basically, once we gather the data, we have to prepare it. We can do this by putting together all the data we have and randomizing it. This makes sure that all of our data is evenly distributed, and the ordering does not affect the learning process because sometimes we have the whole point of machine learning algorithms is that it tries to form this sort of pattern, and if the model actually tries to analyze if there's some pattern or something organized forming around, uh, this might sort of affect the learning process. So we have to always randomize the data. The second part, we have to clean the data. So when we collect data from any sort of external sources out there, it's important that we have to clean the data. So when we clean the data, we want to remove this unwanted missing values, rows and columns, duplicate values, and all sort of data type conversations, because we have to restructure the data and change rows when we want a learning process to be efficient. So that comes to the cleaning part, where we remove unwanted data, missing values, rows and columns, duplicate values, data type conversions, and etc. Next, visualization of the data. Sorry. Yeah, visualization of data. Here we just try to understand to see if the data is structured or not, understand the relationship between various variables and classes that are present. So this is the whole concept of cleaning the data, where we're basically feature engineering and feature selection, where we try to select the necessary X and Y target variables for our model and sort of complete all the data cleaning to just remove all the missing values, data type conversion, etc. And now comes to modeling. Now, modeling is where we actually create our machine learning model here, because again we have our data ready. So now we can start building a model. We build a model based on what problem case statement we're dealing with. Here we have to predict. Here we have to predict what exactly the weather forecast will be in the next few years. For that we already have. For that we can consider this as a regression problem. So because it's a regression problem, we can use a simple machine learning models such as linear regression to follow on. So here we can use linear regression. You can finally train the model, and after that you can do model testing, where once the model has been trained properly, we can test and see if the model which you have trained is working perfectly. So we're basically just checking for the accuracy by testing with newer data in which the training data hasn't really seen. So that really comes in model testing, and finally deployment, where once the whole weather prediction model has been created, we can deploy this sort of model in a web application, Android application, anywhere which we want. So that's really the whole process flow of how machine learning really works. Now, history of AI. Now we have already identified what exactly is the concepts of what AI and machine learning is. Now AI is sort of this concept out there that has seen this basically experienced this several hype cycles, where sometimes people try to hype AI so much that they try to think it's the next future out there, and sometimes AI has been it oscillated so much down that many people sort of thought that AI is sort of this useless concept that no one really talks about it, because the whole history of AI was just this huge hype cycles going this oscillating up and down really. So let's just talk for a bit into what AI has experienced in the history of it and what it really means to us right now. So first, 1950s. This is really when the whole early AI really has started. In 1950, Alan Turing developed the Turing test. Now, this Turing test is mainly used to test the machine's ability to exhibit intelligent behavior. And in 1956, artificial intelligence was accepted as a field at Dartmouth Conference. 1957, Frank Rosenblatt invented the perceptron algorithm. I'm pretty sure you all know what exactly perceptron algorithm is. It is the first sort of neural network ever invented, and this was the precursor to the modern neural network. So any modern neural networks you see like REST architecture, VGGNet, AlexNet, it was all inspired from the whole perceptron algorithm here. And in 1959, Arthur Samuel published an algorithm for a checkers program using machine learning, where Arthur Samuel published this algorithm that can play checkers using machine learning. 1980s. 1980s is really when AI has seen a huge boom out there. One of the reasons was expert systems. Now, expert systems are really just systems with programmed rules to design the whole concept of mimicking human experts. And this sort of expert systems ran on mainframe computers with specialized programming language like Lisp. And this was the first widely used AI technology, with only two-thirds of Fortune 500 companies using them at peak. And in 1986, the backpropagation algorithm. Now, again, we know the whole backpropagation algorithm was also introduced. And now it was able to train this multi-perceptrons, leading to new successes and interest in neural network research. Where from going with a from a single perceptron algorithm, now backpropagation can also train multi-perceptrons, sorry, multi-perceptrons neural networks. And this led to new success and interest in the field of neural network research. In the late 1990s to 2000s, the classical machine learning has started, where the advancements in the SVM led it to becoming the machine learning method of choice because we know how powerful SVMs really are. And AI solutions has success in AI solutions right now has succeeded in spaces like speech recognition, medical diagnosis, robotics, and many more areas. AI algorithms were integrated into larger systems and became useful throughout the industry. And I think you all know about the Deep Blue chess as well. Basically, the IBM has developed something called a Deep Blue chess system that bet the world chess champion Gary Kasparov in May 11th, 1997. So throughout the 1990s to 2000s, machine learning saw this huge sort of boom, not only ranging from backpropagation to multi-perceptrons, expert systems, and also and also the whole concept of many AI solutions that have succeeded in spaces like speech recognition, medical diagnosis, and robotics. And finally, 2012. Now, this is what many people would like to consider as the deep learning revolution. Now, again, there are a few reasons saying Jeffrey Hinton posted publishes a paper on unsupervised pre-trained models that allow deeper neural networks to be trained. This is also the time when neural networks are rebranded into the concept of deep learning. And one of the biggest reasons why 2012 is a deep learning revolution is because of ImageNet. Now, ImageNet is basically a database that contains of human tagged images that was presented at the CVPR conference. And in 2012, these algorithms compete on several visual recognition tasks at the ImageNet competition. Now, ImageNet, I'll just get back to what exactly ImageNet is in a few seconds here. But ImageNet again was a huge revolution back then in 2012. I'll just explain why in a few more slides. Now, deep learning. Now we have got a good understanding to what AI is, what machine learning is, and a bit more into what the history of AI is as well. Now now let's take a look into what deep learning really is. Now, So now deep learning. Now deep learning is again is a subset of AI, but to be more precise, deep learning is a subset of machine learning. Now this is inspired from the way how a human brain filters information. So this is associated with the learning from examples. This is how we as a humans learn. Now deep learning systems help a computer model to filter the input data through layers to predict and classify information. Deep learning processes information in the same manner as a human brain. It is used in technologies such as driverless cars, deep driverless cars, maybe things like sorry, driverless cars, object detection, and even right now translation as well, where using sort of NLP techniques and deep learning techniques, we're able to translate. Now, deep learning architectures are classified into three types: one being convolutional networks for images, recurrent neural networks, and recursive neural networks. Today's session will mainly stick with convolutional neural networks because that's really what the whole concept of computer vision revolves around. Now, deep learning, again, we already know it's a class of machine learning algorithms, but its whole concept is that uses has like multiple cascades of layers of processing used to extract features from data and make that predictive guesses about new data. Deep learning learns with big data, basically huge amount of input examples and trial and error guesses to adjust weights and bias to establish new key features. Now, this is how the whole deep learning process really works around. One being here, we have some real life activities, so sort of the data, the actual gathered data, and then we have we can think of this as database into all this data coming in. We pre-process the data, the whole data cleaning and all that stuff. Now we think about input the algorithm. We select the algorithm, and finally we get and the neural network here trains based on trial and error process. And finally we get that output, basically learn knowledge from that real life activity. Now, now we already understood machine learning is about of deep learning. But what makes machine learning different, or what are the limitations of machine learning? Like what makes deep learning at least better than machine learning in few cases? Let's first understand what the limitations of machine learning is. Now, machine learning is about computers being able to think and act with less human intervention. And we have seen that we have to perform the whole feature selection and feature engineering, right? Now, when we want, like we have seen previously, that if we want to train machine learning model, we have to do feature selection and feature engineering. Basically, we have to select which target variables we need and which target x and y variables we need to develop this machine learning model. But now let's have this statement. Here we have an image of the dog, but now we wanted machine. We wanted a computer to determine if this picture was a dog or a cat. Now, how can that? What do you think a machine learning model? So, what do you think a machine learning model? Like, what features will you use? Now, machine learning is great when it comes to dealing with simple things such as, let's say, Boston House prediction, things like, let's say, like weather forecast prediction. Machine learning is great and all because we select the whole feature selection and feature engineering right there. We know what target variables we need. But now when it comes to something like a dog image here, it's all coming into pixels, like it's all zeros and ones here. Then what features can we really depend on? Now, this is not a problem case statement of machine learning. This here is a problem case statement of deep learning because this is where deep learning comes into the play, where deep learning tries to take this entire image as multiple pixels, tries to have this like CNN, CNN network, and there it has like a bunch of uh, edge detectors, color schemes, and all these different types of uh, all different types of layers that can predict that can classify if this image here is a dog or cat. So this is really what's the difference between machine learning and deep learning is. If we get an image of a car as an input in machine learning, we have to perform the whole feature extraction and etc. And then the machine learning model does the classification. And finally, we get the output saying if this image was a car or was it not a car. But in deep learning, if we give an input image, the whole concept of neural network or deep learning, what it does is it does feature extraction where it understands which features, like which color schemes, which amount of edge detectors we have to use. It performs the classification, and finally we get the output if this image here was a car or was not a car. That's really what the difference between machine learning and deep learning is. Where deep learning knows what are the best features to pick from an input image that can result in giving us the best accuracy. And this whole process of getting the correct sort of features from an image is this basically just takes on a trial and error process, mostly on back propagation. But this is really what makes the difference between machine learning and deep learning. Now let's go a bit more into what the inner working of deep learning here. Let's understand what neural networks are. Much of what makes us human is the power of our brain and cognitive abilities. The human brain again is an organ that gives humans the power to communicate, imagine, plan, and write. Because our if you agree or not, our human brain is definitely a source of magic. Because if you think about it, we as humans, we have this sort of organ that gives us the power to at least talk with other fellow beings, try to imagine new concepts, try to plan maybe something for an event or something like that, and even write stuff. So this organ can actually do so many things that you can be amazed of. And that's what makes us as a human so powerful. And since the brain is primarily made of an organ, it's just interconnected neurons. AI researchers, for anyone dating back to 1950s and 1980s, AI researchers sought inspiration from the brain by recreating the brain structure through artificial neurons. So the whole concept of neural network networks were derived from the inner working of human brains. Just as the same way how a brain was interconnected by multiple neurons, an AI model or something like a neural network was connected by various neurons as well. They could connect simple artificial neurons in complex ways. And the connections of those neurons and artificial neural networks would create more complicated outcomes. And this was the brain network was inspired from the working of our human brain. It was one neuron. So in reality, and sorry, in reality, a brain neuron receives a signal, processes it, and propagates the signal. So it gets the signal, it processes that signal, and then it shoots out the signal to another neuron. And us as a brain is comprised of around 100 billion neurons, each connected to less than 10,000 other neurons. So that's something like 10 power 15 synaptic connections. And artificial neural networks are a simplistic imitation of brains comprised of dense net of simple structures, where we know something like we know something like a artificial neural network is inspired from a brain, but an ANN or artificial neural network is not as powerful as a brain because our actual brain consists of 100 billion neurons, where ANNs are just a simplistic imitation of a brain, just comprised of simple dense nets of simple structures. That's really what neural network or ANN really is. So if you look at how artificial neural network works, it's sorry, it's organized into three layers: input layers, hidden layers, and output layers. As we can see here, we have input layers where the image is actually going in, the hidden layers where the image is going to be processed, and finally output to at least classify what that image really meant. For the image directors, the first values, we can think of these first layers here, the input layers as a visual context, as a rise. And these hidden layers is what we can think of different types. This hidden layers is what we can think of our brain actually firing neurons to understand what this input image really is. And finally, once the hidden layers whole activation function has been completed, we can get a final output saying what the input image really meant. So this is really how an neural network tend to work out. And here, to train a neural network, we need labeled examples or images, something called training data. So we initialize this network weights randomly, and initially we get random predictions. So first, when we train a network, we just randomly initialize weights around, and then we get random predictions starting from input to hidden layers as well. And for each labeled training data point, we calculate the error between the network's predictions and the ground truth. So we're trying to calculate the error between what this network is predicting us and what the ground truth label. So basically the whole difference here. And then we use this back propagation to update the network parameters in the opposite directions to sort of what sort of error we're getting here, and that basically results us a new weights. So this is the whole algorithm uh, when coming into each and every new activation function. When we have a new weight, we have an old weight, the learning rate here. You can think of as alpha into the how much gradient of error increases weight with when we increase the respect to this error with this weight. We multiply this with the learning rate, and then we get the difference between the old weight with this learning rate into the gradient error. And finally, that's how we get a new weight. And this new weight can again check based on trial and error process if you're getting closer to the prediction. So here we can see an example of how a neural network is functioning. Where here we have an input image called handwritten digit called 2, and then we have an output image called 2. And this too goes to neural network, and multiple neurons are firing again and again to find a to comparison, saying this, let's say here one, here we're getting a final value saying this handwritten digit is nothing but one. And that's really how a neural network tends to function. And the fields of deep learning. Now, deep learning again, we right now I might be only working in computer vision, but the whole concepts of deep learning are endless. There are concepts from cognitive computing, computer vision, machine learning, neural networks, natural language processing, and etc. So where deep learning can be used is literally an unimaginable sort of context as well. Speech recognition. Right now we know sorry, speech recognition. Right now, we know speech recognition makes the computer listen, including things like Siri on the iPhone that we can access in our daily life. And in Google Voice Input, you can just say one sentence which turns into a text. Speak to Google Map and say, when I'm going, it automatically generates the entire navigation map route for you. These are some applications of speech recognition. Now, speech recognition can be divided into three aspects. One being speech synthesis, including online and offline speech synthesis, speech recognition, including speech dictation and other aspects, and semantic understanding, where it's mostly used for neural networks to extract the meaning of speech, including the voice evaluation, and some features mainly commonly used in machine translation as well. And currently, what I'm working with, computer vision. Now we already know computer vision makes the computer see. We hope that computer can replace some of the functions of the human eye. For example, there is a very useful document analysis technology called OCR. You probably might have used it when you want to scan documents. We can let the computer scan the document and read it. For example, we can get an invoice of some pay slip or something like that. So the computer can immediately scan it, extract the information about the let's say of something about the amount, tax rate, etc., etc., and then then based on what sort of values it gets, it then just presents that in a digital format which we as humans can which at least something in a digital format which we can send out in emails and etc. And computer vision doesn't really just stop on that. There's like many things: object recognition, detection, object movement tracking, and etc. as well. Then there's also NLP, which isn't really my sort of area, but NLP works around with deep learning as well. And a bit of I'll just give a small introduction to computer vision because it's really what it's about in actually what about the session is into. So, computer vision is a field of artificial intelligence (AI) that enables computers and systems to derive meaningful information from digital images, videos, and other visual inputs, and take actions or make recommendations based on that information. If AI enables computers to think, computer vision enables them to see, observe, and understand. Again, the whole field of AI and computer vision is that it enables computers and systems to really see. And with what the visual inputs is getting from that view, it takes those into actions and makes and tries to make uh, and tries to make problem case statement solutions based on that visual input. And because the system is trained to inspect products or watch a production asset can analyze thousands of products and process in a minute, noticing these impossibilities, defects, or issues, it can quickly surpass human capabilities. In 2015, there has been research done that in object detection, computer can actually perform better object detection than what we as humans are. And not just that, I basically recently participated in a leaf counting challenge where my model got a mean absolute error of 0.56 MAE. At least I remember it's 0.56 mean absolute error. And in that, basically, we have a bunch of images of leaves and accounts of the leaves. So the whole concept, the whole thing which I have to do is I have to predict the number of leaves in an image. And if I were to compare this with someone like a human, my model was doing better than what a human was counting leaves in an image. That's because computers tries to find these patterns of leaves can identify it better. Now, computer vision is used in industries ranging from energy and utilities to manufacturing and automotive. And this market of computer vision is expected to reach at least 48.6 US bill- sorry, 48.6 billion US dollars by 2022. And if we actually check the market forecast and analysis, this values can even go higher and higher as the years increase. This is a huge correlation between the market increase of computer vision and what the industry is looking for right now. And one of the biggest reasons why computer vision saw this huge growth or this whole deep learning revolution was because of ImageNet. Now, ImageNet is this large data set of annotated photographs intended for computer vision research. And the goal of developing the data set was to provide a resource to promote the research and development of improved methods for computer vision. The whole general challenges task for the ImageNet for most of the years were as follows: where image classification. So in image classification, we have to predict the classes of objects present in one image. Single object localization, where not only we have to not only we have to do image classification, but draw a bounding box around that specific image. One example would be each box at each object at present. And object detection, where here we're getting where here we're doing image classification, plus we're drawing this bounding box for each object present in that specific image. But that's really what exactly ImageNet does. So ImageNet is just a huge data set of these annotated photographs, and most of the times people tend to use ImageNet to image to at least challenge how well their algorithm does. So that's one of the reasons why ImageNet was created. The biggest and ImageNet was the biggest revolution at that time, because one of the reason was we had this whole one place structured data where anyone can come and start using these images to build an object detection model in at least hours. Some people can start doing image classification. Some people test their models, they'll test their algorithms to see how well it's doing currently with ImageNet. So these are different types of like deep learning models used in ImageNet. Now these all were CNNs, there are things like SCNN, ResNet XT, Inspection V4, etc. And now, one of the biggest, one of the best models created at that time was AlexNet. If you ask me why it's the best model, you can see, or you can just see the rise of AlexNet immediately, where we see something called NEC, XRC, and you see AlexNet with the error of 25.8 to at least 16.4. So that's some so if we see something like 4% of error, sorry, a 4% of error decrease right there, and that's what makes AlexNet so powerful. And right now, one of the most popular models are SCNet, ResNet, Inception V4, and ResNet architecture. But Inception, but the whole AlexNet here was the biggest revolution for this whole ImageNet solutions out there. And that's mostly about ImageNet. But now let's see the applications of computer vision. Now we understand what computer vision is, we had looked into what deep learning is, and we looked into various ImageNet models as well. But how far does the extent of computer vision really go? If we talk about applications of computer vision, right now we have concepts revolving around visual navigation, augmented reality, optical character recognition, panorama stitching, 3D reconstruction, games, 3D object recognition, surveillance, segmentation, inspection, etc. So when you talk about applications of computer vision, the whole context is endless. There are like at least a bazillion number of applications where computer visions can be useful for companies. And if we talk about companies, these are the amount of companies that are using computer vision right now. We have big companies from Facebook to Google to Microsoft to NASA, Intel, who tend to use computer vision in their daily operations. Even companies like Tesla for self-driving cars, they're using computer vision. And this whole drain of computer vision is not going to end off soon, and it will not it will not melt off soon as well, because the better and the bigger amount of data we should be receiving in our daily life is going to result in the better and the bigger amount of visual cortex machine learning models is going to be increasing as well. So for that, what skills do we need for deep learning and computer vision? Because we know deep learning and computer vision is an increasing field out there. What skills do we need to get accumulated with these concepts? So for that, mathematical skills. One being mathematical skills are going to be very useful for deep learning and computer vision, because we at least want to know how. Because in things like deep learning, there's going to be a lot of mathematics involved. This can be into calculations, like things like linear algebra, calculus, and etc. And programming skills, because again, without programming skills we cannot train a deep learning model. So we at least need to have a good expertise of knowledge with things like Python programming, R programming, etc. And data engineering data engineering skills, because when we're dealing with something like images or any sort of uh, data format out there. We need to have a good conclusion or good working skills with it to how exactly should we clean the data, should we pre-process the data, and etc. So we need good data engineering skills and machine learning knowledge, because again, deep learning is a subset of machine learning. So we want a good amount of machine learning knowledge, and then we have to know how to deal with vision data, because a normal data like CSV text, I think this might be at least uh, this might be at least easy to complicated. Sorry, this might be at least easy to complicated to deal with with text data. But when it comes to vision data, uh, sorry, it takes a lot of computing power, mainly because even if the object in an image, sorry, sorry, if the object in that image will be at least scaled to a few centimeters away from the actual focus point, the entire knowledge of the image is going to be changed. I think vision data is such a sort of complicated yet such challenging task to deal with in current deep learning and computer vision scale right now. And we also need to have good knowledge of working with deep learning algorithms like the new architectures like ResNet, Inception, V2, etc. And we also need to have a good knowledge on deep learning frameworks, because deep learning frameworks are right now the bomb, mainly because using these deep learning frameworks we can actually do any sort of skills such as maybe classification, object detection. So a few famous deep learning frameworks are PyTorch and TensorFlow. I mainly use TensorFlow, but PyTorch is also a great framework to go ahead with. But that's really what mainly comes to end of today's session, and I hope hopefully you all got a great understanding to what deep learning and computer vision what deep learning and computer vision is. A good understanding to what AI, the history of AI, the whole concept of machine learning versus deep learning, like why exactly deep learning is needed, and maybe a bit more understanding into what makes computer vision such a huge power tool right now. So hopefully you have at least gained some good insights from today's session. If you want to connect with me or follow me, you can connect with me on LinkedIn, Facebook, Instagram, and Twitter. But yeah, so yeah, thank you everyone. You have been a great audience. Yeah, thank you.
Students, feel free to ask your doubts. If you don't have any doubts, let's move to the
Good
vote
evening,
of
sir.
vote.
Yeah, actually, is there any device needed for computer vision, like camera, to detect that object?
Well, it mainly depends on the use case. For example, let's say if it's a self-driving car. If it's sort of something like a self-driving car, in that I'm pretty sure image is not the only thing to take into the place. Maybe there are like a bunch of sensors, maybe things like things like voice as well is going to be taken place. So there's based on a dependency, there might be certain cameras and certain voice devices we use to, let's say, we use instead of computer vision. But if it's something, let's say we have a drone and we wanted to fly that drone, and if we wanted to use that drone for object detection, then yeah, it's a simple JPEG and a PNG image that we are basically getting as an input, and with that input we can do any sort of object detection. So sometimes based on the dependency, the device might change it, but most of the time it's just JPEG and PNG images.
Yeah, for object detection, we have some sensors, right? How can this computer vision different from those sensors?
Object detection mainly it just falls upon using bbox annotations of data and JPEG images. If there are such, just I'm not sure if there are. I guess based on sometimes the problem key statement, they might include sensors. But if we are dealing with things like sensors and image data and all these things as well, then we might have to develop then we have to have another space in the deep learning model to have the visual cortex in it. So we have to maybe change the model in a way where it accumulates not only the whole concept of what you see the vision, but also like let's say some other senses as well. So we have to design the model in that way. But most of them, simple classification, simple object detection models, they only need just images. That's it. Like from a mobile camera to even like a laptop web camera, anything really works.
Thank you. Thank you, sir.
How did you start your journey as a data scientist? Actually, I got my first job as a data scientist at the age of 12 with Montage Smart Business Solutions, was a digital marketing company. Mainly to actually get this sort of data science job, I guess Kaggle was a great tool actually. Uh, Kaggle is really useful mainly because it has many sort of data sets, challenges, and tasks out there. So when we sort of solve these data sets, like these tasks and challenges, we sort of gain more understanding into how to develop a good model, like how to at least get a good understanding of how to visualize a problem. So the more number of Kaggle data sets Kaggle challenges I solved, I got a better understanding to how I can build my own models, how I can do data engineering myself, and etc. So, and that too with a lot of skills from like good skills from Android these machine learning course, different types of competitions and etc. I got a sort of I went into an interview as well, but that's really how I got skills I would say required for data science.
Okay, students, let's wind up our session. Now I'll hand over my mic to Bhargavi to express vote of thanks.
Vote of thanks. On behalf of Tripless and students, I am glad to be standing here to express my vote of thanks. A special thanks to our guest speaker, Mr. Siddharth Pili, for accepting our invitation and for being here with us today. Your thoughts have truly inspired us, sir. I thank our Honorable Director, sir, and Dean Academics, HOD, sir, Faculty Coordinator of Tripless, for supporting the faculty members. Thank you all. This is the end of the session.
Yeah, thank you.